In this video, we're going to look at a different kind of factoring called factoring the sum and difference of cubes. So to help get us motivated, we're going to start with a multiplication problem because remember, factoring is just undoing multiplication. All right, so here we go. Let's try multiplying the quantity a plus b times the quantity a squared minus ab plus b squared. It'd be good practice for you to pause the video and multiply this together and see what you get. And when you're ready, start the video again. Alright, so to do this, we're just going to use the distributive property. So the first thing I'm going to do is multiply a by each term. So let's go ahead and do that. That's going to give me a to the third power minus a squared b plus ab squared. All right, then I'm going to take b and multiply that by each of the terms in the second set of parentheses. And that's going to give me a squared b minus ab squared plus b to the third power. All right, how does that simplify? Let's see what we've got going on here. Well, we've got a minus a squared b and a plus a squared b. So those are going to cancel each other out. And then we've got a positive ab squared and a negative ab squared. So those are going to add to be 0 is probably a more appropriate way to say that. Those will add together to be 0. So all we're left with is a to the third plus b to the third. All right, so this is an important fact that if I multiply these two things together, I get a to the third plus b to the third. So what that means is I can factor a to the third plus b to the third into these two products, so the product of these two expressions over here. I'm going to write that out a little bit nicer over here so we can work with it without all the lines, and then we'll do a factoring problem. Actually, let me get a little more room here. Okay, let's write it right up here. Okay, so what we just learned is that a to the third plus b to the third is the same as a plus b times a to the second minus a times b plus b to the third. And we learned that by literally doing this multiplication. All right, so what that means is we can go the other direction and factor something back out. And this a and b can be any number, positive, negative, variable expression, all right? It can be any number. So let's do an example here. Let's say I have something like x to the third plus 8. Now you might not recognize right away that 8 is something to the third power. And factoring these kind of problems is going to be a lot easier if you can recognize perfect cubes. So let's just go over here for a second and write down perfect cube numbers. All right, you've heard of perfect squares before. Well, we also have perfect cubes. So 1 to the third power is 1. 2 to the third power, 2 times 2 times 2 is 8. 3 to the third power, 3 times 3 times 3 is 27. 4 to the third power is 64. 5 to the third power is 125, and you could continue. But these numbers come up a lot when you're dealing with perfect cubes. As far as the variable expressions go, I'm going to write this out a little more detail because this can be a little confusing. We can have x to the third power, which is obviously x to the third power. We could have x squared to the third power, which is x to the sixth. Okay, so that makes x to the sixth a perfect cube because it is x squared cubed. What if we took x to the third and cubed that? Remember, you multiply the exponents here, so that's x to the ninth. X to the ninth is a perfect cube. Let's do one more and we'll look at the pattern. X to the fourth cubed, multiply those, we get x to the 12th. So as far as the variables go, if the exponent is a multiple of 3, that makes that variable expression, that variable product or factor, a perfect cube. All right, so here we have x to the third, that's a perfect cube, and we have 8, that's a perfect cube. So we could think of this x to the third plus 8 as x to the third plus 2 to the third. To factor it then, we'll go up here and use this fact that we just showed was true, and we will let x be our a value. So x is like our a value, and 2 is our b value. And then all we do is just plug it in to this formula right here. Okay, so a plus b is going to be x plus 2. A squared, our a value is x, so that's x squared, minus a times b, so 2 times x, so minus 2 times x, plus b to the second power, that should say. This was b to the second power. I think I just wrote it wrong. Hopefully I didn't say it wrong. That should be b to the second when we multiplied that out. So b to the second power is 2 to the second power, which is 4. All right, and that's your answer. That's how you factor it. Okay, so it's kind of just a matter of using the formula and plugging stuff into the formula correctly. And proving this formula wasn't hard, right? We just multiplied these two things together. Now, if you wanted to check this, just like any factoring, you can check by multiplying this stuff back together. Let's just do it once. I know it's a little time consuming, but it kind of convinces you that what you have is actually correct. All right, so if we did this right, if I multiply these two things together, I should get x to the third plus 8. Let's give it a try. If you want to pause the video and try it, I think that's a great idea. So we get x times x squared, x times 2x, all right, and then x times 4. I'm going to use a little technique here that you may have seen right underneath. Then I go to the 2 times x squared, so I'm going to write that under here. 2 times negative 2x, and 2 times 4. Well, we can see this stuff lined up here. The x to the third is there. These guys make 0. Those guys make 0. And we're left with the 8. And it worked. All right. So if you're asked to factor x to the third plus 8, your answer is this guy right here. That is the answer to that factoring problem, because you've broken it down into two things that multiply together to be x to the third plus 8. Well, as you might imagine, there is a similar formula. Well, maybe you won't imagine, but we can show you. There's a similar formula for subtracting cubes. I guess we shouldn't take that for granted, because remember when we did squares, we had difference of squares, but we don't have the sum of squares. So let me show you that one. Let's go down here and let's multiply a minus b times a squared plus ab plus b squared. Alright, so if we multiply that together, I'm going to take a and multiply it by everything in the second set of parentheses. So we get a cubed plus a squared b plus ab squared. Now I'm going to multiply negative b, or the opposite of b, times everything in these parentheses. So negative b times a squared gives me that. I'm going to write it in this order, so you know the letters are in alphabetical order. That makes it easier to see the like terms. B times ab, the negative times a positive, gives me a negative ab squared. And b times b squared is b cubed. Negative times a positive is a negative. Alright, so that gives us a cubed. That makes 0, that makes 0. Think of adding this together. 0, 0, minus b cubed. Alright, so there's our other formula. This thing times this thing is a cubed minus b cubed. So these two formulas up here in blue are called the sum and difference of cubes formulas. And anytime you see a sum or a difference of cubes, you can use those to factor your binomial. All right, so these are binomials. These are special binomials. These are perfect cube binomials. I know you've done perfect square binomials, and I've mentioned that again. So let me just go down here and make this clear. All right, so we have something like that. That's a binomial. That's a perfect square binomial, because x times x is x squared, and 4 times 4 is 16, and 1's a plus and 1's a minus. That's how you factor perfect squares. All right, this is perfect cubes, so you need to recognize that they're cubes and approach it a little bit differently. All right, I have two more examples to show you because it can, these can get a little bit tricky setting it up. So let's do two examples together. Let's see, how about green? Green's exciting. So let's say we do 125 minus y to the 6th. Okay, so the first thing you have to ask yourself is that the difference of squares? Is it the difference of cubes? Does it have a greatest common factor? So we look at y to the 6th and we, okay, well, that's over here on our list, x to the 6th. So y to the 6th is y squared to the 3rd power, so that makes it a perfect cube. Y to the 6th is y squared to the 3rd power. It's also y to the 3rd to the 2nd power, so it's a perfect square as well. Okay, so y to the 6th could be difference of squares, could be difference of cubes. So that, now we got to check out the 125. Well, 125 is 5 times 5 times 5. That is a perfect cube. It's not a perfect square. Okay, so we're going to use the difference of cubes. And what's your a value? Think about what your a value is. Not 125. Your a value is what cubed gives you 125. And sometimes it helps to write like this, okay? What is it? Actually, you know what? I'm going to use a different color there. Let's use purple. All right, so that's your a value. And then what goes in there? Oh, let's do red. Y squared to the 3rd power. Oops, I wanted green. Undo. Green y squared to the 3rd power. So the y squared is your b value. Okay? So now all you got to do is go up to this formula here, and wherever you see an a, you're going to put a 5. And wherever you see a b, you're going to put a y to the 2nd. Okay? Let's do it. Here we go. I'll do it on this line here. So a minus b, so that's 5 minus b, which is y squared, times, I think I'm going to need a little more room over here, so let's get rid of this. So now I have to do a squared, so that's 5 squared. I'm not going to do it out just yet, just for clarity here. I'll write another line. Then a times b, so 5 times y squared, so 5y squared, plus b squared, and my b value is y squared. My b value is y squared, and I have to square that. B squared, and b is y squared, okay? So your final answer, if you write it out, would be 5 minus y squared times 25 plus 5y squared plus y to the 4th. All right? Okay, let me show you one more. This one has something different about it. Let's do 54 x to the 4th minus 2 x y to the 3rd. And you're looking at that and you're thinking, what is going on? That doesn't even look like the difference of cubes. 2 is not a perfect cube. 54 is not a perfect cube. But what is going on there is a greatest common factor. Right? You always need to look for a greatest common factor. What is the greatest common factor? Let's see. Well, 2 goes into 54 and 2. Oops, I didn't want to write that parenthesis yet because something else goes in there. What else goes in there? Besides 2, what is a common factor of both terms? They both have an x. Okay, can you think about what's going to be left when we take out the 2x? You got it? It's going to be 27, because 2 times 27 is 54, x to the third, because x times x to the third is x to the fourth, minus the 2x is gone, and we have y to the third. Now, what's left in these parentheses is the difference of cubes. So, you write down the 2x, and now you're going to factor this difference of cubes using this formula right there, that formula, because we have a perfect cube minus a perfect cube. All right, what's our a value? Sometimes this helps. Our a value is whatever cubed gives you 27x cubed. So our a value is 3x, because 3x times 3x times 3x is 27x cubed. Our b value is simply y, right? Our b value is simply y, because we have y cubed. So up here, wherever I see an a, I'm going to write a 3x. Wherever I see a b, I'm going to write a y. So that's going to give me 3x minus y. I just did a minus b. Now I have to do a squared. So 3x squared would be 9x to the second. 3x times 3x is 9x to the second. Then I have to do a times b. So 3x times y is 3xy. And then lastly, y squared, which, since b is y, is just y squared. Whew. All right, we did it. So you can find the sum and difference of cubes in problems that contain other types of factoring as well. Always look for that greatest common factor first, because sometimes the problem is not clear until you take out that greatest common factor, and then you see, oh, well, what's left here looks a little bit more manageable. All right, I hope that helped, and good luck with your sum and difference of cubes.